A cubic function f is defined for x an element of R as f of x equals x cubed plus 1 minus k squared times x plus k, where k is a constant. Show that minus k is a root of f. So here's f of x using the standard function notation that we will use. And we want to show that minus k is a root, so we want to get f of minus k. So we replace x with minus k. So we have to take minus k and cube it. So we write minus k in brackets here. We want to cube this quantity. So replace x with minus k, and if we simplify all of this, we should get 0. If minus k is a root, then f of minus k should equal 0. Minus k times minus k times minus k is minus k cubed. Multiplying by minus k in here gives us minus k plus k cubed. And then we have a plus k. We get a lot of cancellation here. All of this is 0. So that shows that minus k is a root. Is a root of f of x equals 0. It probably should say a root of f of x equals 0 to be more precise. Find in terms of k the other two roots of f. Well, here we use the factor theorem. If minus k is a root of f of x equals 0, it means that x plus k is a factor of f of x. So if we have the root, we just change its sign and write x in front of it, and then we have a linear factor of f of x. That means x plus k divides into f of x and leaves no remainder. So to get the other factor of f of x, we need to divide the linear factor x plus k into f of x, and the other factor will be a quadratic factor. From that quadratic factor, we can find the other roots of f of x equals 0. So the first step is to divide x into x cubed to get x squared, then multiply x squared by x to get back the x cubed. X squared by k gives us kx squared. So that's the multiplication step done. The next step is to subtract. So we divide, multiply, subtract. X cubed minus x cubed gives us 0. We want to take this term here and subtract this term. So we take this and subtract this. Well, there is no x squared term. You could write 0x squared up here. So to be 0x squared minus kx squared gives us minus kx squared. What I had written down here was correct, but I want to do this a little bit more precisely to make clear what's going on. It's probably a good idea, if you get a term that's different from the term that's above it, to write in a like term. So we got kx squared here from multiplying x squared by k. So it's a good idea to write 0x squared up here so that we can combine like terms. 0x squared is of course just 0, and then write the remainder of f of x over here. So when we subtract, these give us 0. We get 0x squared minus kx squared. So that's going to give us minus kx squared. So that's the subtraction step actually done. When we've taken the result of the multiplication, which was x cubed plus kx squared, and subtracted it from f of x by combining like terms. And if a like term is missing, just write it in, write 0 times it. Like we had no x squared term in f of x, so you need to write in 0x squared. So that's the subtraction step done. The next step is to take down the next term in the expression f of x. Now the next term is actually this term here. So let's just write it down here. Okay, this is what we had before, but it wasn't very clear. I wasn't following the exact procedure to get to this, but it was correct. Anyway, now we take x and we divide it into, well, normally into this term, but we could actually divide it into this term, I think. But let's divide x into minus kx squared. Well, that's going to give us minus kx, because minus kx times x is minus kx squared. So now multiplying, we get minus kx squared. Minus kx times plus k is minus k squared x. Now we're going to have to subtract here. So we need to combine like terms. Well, this bracket here could be written as x minus k squared x. If you want to, you could multiply x into the bracket here, but I won't bother. Anyway, subtracting, we get 0 here, of course. We get 1 minus k squared x plus k squared x. I'll just write that down. 1 minus k squared x plus k squared x. So I've taken this term and added this term on. And if you multiply the x in here, of course, you're going to get 1x minus k squared x plus k squared x. So the k squared x's will cancel out, and we will just be left with 1x. So that's the subtraction done. And the next step is to take down the next term, and we just have one term left, which is k. So here we have x plus k. And now we go back to dividing. Divide x into x, goes once. Then we multiply 1 by x, and then 1 by k. And we get x plus k, and that's a good sign, because when we subtract here we get 0. Eventually we have to get a remainder of 0, because we know from the factor theorem that x plus k is a factor of this expression f of x. So we factorized f of x into two factors, a linear factor x plus k and a quadratic factor x squared minus kx plus 1. Now here is another method for finding the quadratic factor. From the factor theorem, the linear factor is x plus k, and if we multiply x plus k by a quadratic factor in x, we have to get f of x. So here's f of x written out, and there is no x squared term in f of x, so I've written in 0x squared because we're going to compare both sides. So the quadratic factor in x we do not know, so we just call it ax squared plus bx plus c. It has this form. A quadratic expression has this form. We just need to find out what a, b and c are. We know that if we multiply this out, we have to get the right hand side for all values of x. So this is an identity. So sometimes with an identity you will see an equal sign that looks like this, which means that it's an equation that's true for all values of x, not just some values of x. Okay, so this is an identity, so we just multiply it out and compare coefficients on both sides. If we multiply x in here, we get ax cubed plus bx squared plus cx. Multiplying k in gives us ka x squared plus kbx plus kc. Let's just simplify the left hand side, gather up all the like terms. Well, we've only one x cubed term. We look at the x squared terms, we have two of them. I'll factor x squared out of bx squared plus kax squared. This should be ka. And now factorize x out of these two terms. C plus kb times x. And finally the constant term that does not involve x. Well, you can see it's just kc here. As a matter of fact, we could have set a equal to 1 here. Why is that? Well, x times x squared gives us 1x cubed. We have to get 1x cubed, and the only way to get 1x cubed is by multiplying the x term by the x squared term. So I could have made things a bit easier by setting a equal to 1. So I can rub out this a here, because it's a 1. K times a, k times 1 is k. So it simplifies down a bit. The constant terms on both sides must equal as well, so we get k times c. It's a constant term on the left hand side. The constant term on the right hand side is k, so that tells us that c must equal 1 actually. So you can kind of work ahead if you like. C is 1. So now we compare like terms on both sides. So the x squared term on the left hand side is this, the x squared term on the right hand side is this. We have an identity, so both sides must equal for all values of x. The only way that can happen is if the coefficients of like terms are the same. So we must have b plus k equals 0, which tells us that b must equal minus k. So b is the value that we just made up, or the k is a given. K is part of the function. So b equals minus k tells us what our quadratic factor must be. So this quadratic factor has to be x squared plus b, which we now know is minus kx plus 1. So there's a quadratic factor. So now, what have we done? Well, here is our equation f of x equals 0. We're looking for the roots of it. We have factorized this equation into a linear factor and a quadratic factor. The product of these must be 0. The only way that a product can be 0 is if either factor is 0. So if we set x plus k equal to 0, we get x equals minus k. That just gives us back the root that we were given at the very start. Now, another way to get 0 is if the other factor is 0. See, if this is 0 or if this is 0, we have 0 in a product. That's the beauty about having 0 on the right hand side. Then we can set each factor equal to 0. So here we go, we can solve this quadratic equation now and find other values of x that are roots of f of x equals 0. So to solve this equation, we note that a is 1, b is minus k, c is plus 1 in this quadratic equation. So we have minus b as minus k, plus or minus the square root of b squared. If we square this, we get k squared minus 4 times 1 times 1, all divided by 2 times 1, which is 2. So these are the other two roots of k. We can't really break this expression down. We could factorize k squared minus 4 into k minus 2 times k plus 2. But we can't do anything with it because the two factors of k squared minus 4 are different. We can't take the square root. So we have to leave our answer like this. If you like, you can write down the two separate values of x. One value is k minus root k squared minus 4 over 2. And the other root is k plus the square root of k squared minus 4 all over 2. So we found three roots. 1, 2, 3. This is a cubic equation, an equation of degree 3, so there can't be any more than 3 distinct roots. If you want to check your solutions, you can go here and type in the cubic equation, hit return, and you'll get the input here if you want to check that you inputted it correctly. And if we scroll down here, we're not interested in integer solutions. We want solutions for the variable x. So here are the three solutions that we got. In part C, we want to find a set of values of k for which f has exactly one real root. So how do we ensure that this equation has only one real root? Well, we take a look at this factor here, and we want this factor to have no roots, no real roots. By setting this factor equal to 0, we know we get x equals minus k. So one way to do this problem is to get a root from setting the linear factor equal to 0. That'll be our one and only root. And then imposing a condition on this factor to have no real roots. So we just end up with this root minus k. So how do we ensure that this quadratic equation has no real roots? Well, we look at the discriminant, b squared minus 4ac. That's this quantity here. These are the roots of the quadratic equation that we got in the previous part. So if we make the discriminant negative, less than 0, then we're getting the square root of a negative quantity. And this entire quantity is not going to be a real number. It's going to be a complex number. So we want b squared minus 4ac to be strictly less than 0. We want it to be negative. And of course, if we calculate b squared minus 4ac, we get the k squared minus 4, the thing in the square root under the square root sign. We want it to be less than 0. So we solve this inequality. So we want k squared to be less than plus 4. Now, we have a quadratic inequality here. We could solve it formally by having 0 on the right hand side. You know, we would get k squared minus 4 less than 0. We solve this by first considering the equation, we consider the equation k squared minus 4 equals 0. Solve this, we know we get two solutions, plus or minus 2. And then we draw a sketch of the quadratic function. I'm just rushing through it now. We draw a sketch of, say, y equals y against k, where y is k squared minus 4. We know that it crosses the k-axis at plus or minus 2. These are the roots of the quadratic equation. So say minus 2 is here, plus 2 is here. So k squared minus 4 would look like this. And then we want to find the values of k for which y, where y is k squared minus 4, is less than 0. And you can see that the values of k that make y less than 0 are strictly between minus 2 and plus 2. So the solution to this inequality is minus 2 less than k less than plus 2. So that would be the formal way of doing it that we've covered before. But you know, if you just have a quantity squared less than some number, you just get the square root of the number and realize that the square root can be positive or negative, and that the quantity has to lie between those two. If you think about it, any number between minus 2 and 2 when squared will give a number less than 4. So as long as k lies strictly between minus 2 and plus 2, then the equation f of x equals 0 has only one root, and it is x equals minus k. It is only one real root. These roots will be complex, and we don't want complex roots in this problem.